And then they realized that they are, in fact, botany majors. Okay, so let's do another tetrapeptide. Since we did easy, let's do hard. H is histidine. A is still alanine. R is arginine. I like to put arginine in problems because it's arg. And D is aspartic acid. What?
I don't know why, but that was so funny.
I amuse myself. You can write down arg, I don't know how to do this problem, and then take a 0. It's great. So this is histidyl alanyl arginyl aspartate, or aspartic acid, his ala ard asp. You always put those little dots in there. This one actually has 3 of the amino acids that start with A in it, right? And you can see that since alanine has already taken the 1-letter code A, that's why arginine has to be R. Why aspartic acid is D, I'm not sure, but it makes sense that once aspartic acid is D, the glutamic acid would be E because it's the next letter, and it's just different by 1 CH2. Generally, the thing is like the second letter, although lysine is K, and there's no K in its name, so whatever. So we can do this one, if we know what the side chains look like. Well, we know alanine, 3H3. Arginine is one of the more complicated ones. It's got 3 CH2 groups, and then it's got a guanidine group. Which is pretty damn basic. That lone pair is the basic pair. It's the one that's attached to the pi bond. Because if you protonate that, you can then resonate onto the carbon and all 3 nitrogens. The pKa of the conjugate acid here, which is the pKa of this thing, pKa of that hydrogen is 12.5. Aspartic acid we already looked up. pKa of that hydrogen was 3.7. We're actually going to need to know the pKa of the C terminus as well. And you might guess it for aspartic acid because it's got the 2 acidic functional groups. That one's going to be fairly low. It's 2.8. And then we need to know what histidine looks like. It's got the CH2 group, and then it's attached to an imidazole ring. And that one is on the second page. So the imidazole ring looks like this. The basic lone pair is this pair again. Because if you protonate that, you can also resonate it onto this carbon and that nitrogen. Usually the basic lone pair is going to be the one that is on the nitrogen with a double bond. And it's definitely not that one, because that one's part of the aromatic system. So the imidazole has nitrogens in positions 1 and 3. The thing that's hard to remember about histidine is that the CH2 is next to the NH group, not next to the N that doesn't have the hydrogen on it. And if we look up the pKa of the conjugate acid of that, it is 6.1. So the conjugate acid looks like this. That pKa is 6.1. And then we also need to know the N-terminal pKa for that one, and for histidine, that N-terminal pKa is 9.2. So you can see it's a little different, right? It was 9.7 for the glutamic acid. So now we can go about writing this at physiological pH and calculating its isoelectric point. Start on the left with the N-terminus, H3N plus. Draw the peptide chain. So there will be 3 peptide bonds. Right, so there's 1 peptide bond, there's a 2nd peptide bond, there's a 3rd peptide bond. And then I'm going to put on side chains. Where are the hydrogens? Back, up, back, up. It doesn't actually matter if you start with the vertex pointing up or if you start with the vertex pointing down. I started with the vertex pointing up both times, but that's just my habit. And then we slap the side chain on there. Right, so this is next to the NH. I want to write it in the fully protonated form, so I'm going to draw it like that for now. Right. This is alanine, CH3 group. This is arginine, CH2, 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 and then that guanidine group. Protonated. So that's the fully protonated form. What's the charge on the fully protonated form of hard? Everybody protonated. +3. How many hydrogens can we take off if we take them all off? Carboxylic acids, one of those, that guy, one of these. So how many pKa values are there that I need to worry about? And I can write them next to them right now that I have them all. This pKa is 9.2. This pKa is 6.1. pKa is the one that's 12.5. That's the most basic of them all. pKa of the terminus was 2.8. pKa of that one is 3.7. I hope I pressed record. Good, I did. I do some other ones in the pre-recorded videos as well, so there's more review possible. So which do you want to do first? Drawing it at physiological pH or calculating the isoelectric point? Drawing it first. Okay, so does the N-terminal proton stay on or not? It stays, it's above 7.4. What about the imidazole? Protonated or not? Maybe a CH2 in there. I lost the CH2. It'll go. So this is a lone pair. That's a neutral side chain. Alanine, of course, has a side chain that doesn't come off, so worry about it. What about this one? Protonated or not protonated at physiological pH? Stays protonated, the basic side chains usually do. What about the 2 carboxylic acids? Protonated or deprotonated, the 2 carboxylic acids? Generally true of the carboxylic acids, right? The acidic side chains, well below 7. The C-terminus almost always deprotonated at physiological pH. So most of the nitrogen-containing side chains stay protonated, arginine and lysine. Lysine is 4 CH2s in an NH2 group. And the pKa of its conjugate acid is, damn, it's not as high as 12.4, but it's pretty high. So lysine generally stays protonated as well. Its pKa is 10.5. Above physiological pH, but the glutamic and aspartic acid side chains get deprotonated. Tyrosine, it's an acidic hydrogen, but it stays protonated because it's above. Cysteine, the other one, which is CH2SH, that pKa is around 8-ish, 8.2, question mark. That one stays protonated at physiological pH. So what's the charge on the peptide at physiological pH in solution and aqueous solution? Have 2 minus charges, 2 plus charges, so it's net neutral at physiological pH. So now we need to do the PI. And so we need the 2 equilibria that involve this one. We don't care about this, or this, but we do care about these. If I took all of the protons that could come off, what did we decide it would be? Charge? -2, right? 5 pKa's to worry about. I'm going to write them out as pKa's this time instead of Ka, because we're actually going to use the pKa's to calculate the isoelectric point. So which of the 2 pKa's I care about? So So I don't care about the first two protons that come off, which are the C terminus, which is almost always the first one off, and the acidic side chain. I care about the third one, which comes off, which is the histidine, and then I care about the fourth one that comes off, which is the N terminus. So I'm basically, formally, I'm writing the equilibrium between this protonated form and the structure I have here, and between this structure and the one that loses the N-terminal proton. But I don't want to write those, so I'm just going to write it out like this. So my PI is equal to the sum of those, 6.1 plus 9.2, divided by 2. Why can't I do that? 7.75. Is that right? No. That's 15.3 over 2. 7.65? I think that's right. So it's a little above physiological, but not much. Which makes sense because of physiological pH, we've determined that mostly it's going to be the neutral species. Right? So it makes sense that the PI would be somewhere near physiological pH. So we only care about 2. We only ever care about 2 of the pKa values. And it's the 2 that involve the neutral species as part of their equilibrium. Yeah?
So basically, like every time with this, whatever the new structure is that we deprotonate the ones that we're supposed to.
Yep.
Like we go about choosing. Like we chose the last one from the last problem as +1. Do we always choose like this neutral and the +1 and negative one, or is it?
Yes.
So every time it's like one or the other. But it's
and in this case, it happens to be the third and fourth protons that come off, whereas in the other one, since the maximum charge was +1, it was the first and second one that come off.
Yeah.
So it's going to be different.
Is that because the neutral charge is in both of those?
Yes.
Okay.
It's because if we want these two concentrations to be equal to each other, they're going to be negligible concentrations of the higher charges. Right? It's going to be mostly the neutral species with some in the +1 and some in the -1, and basically none in the +1, +2, or +3. Because when we derived the equation, right, we wrote this as +1 is in equilibrium with 2 hydrogen ions and the -1 species. Right? So those are the 2 species that are involved in that equilibrium reaction from which we derive the equation. So it'll be different ones depending on whether you have more acidic side chains or more basic side chains. If you have more acidic side chains, you would expect the PI to be fairly low. If you have a lot of basic side chains, you'd expect the PI to be fairly high. So it would actually be a fairly small matter to separate easy and hard because their PIs are so different. Right? You could put them on an electrophoresis gel and have a pH gradient, and they would migrate to the place on the gel where they are neutral, and then stop there, and there'd be a large distance between the two. So there's a bunch of stuff in chapter 6 about protein secondary and tertiary structure and folding and alpha sheets and beta sheets and alpha helixes and all that kind of crap. We're not going to talk about secondary or tertiary structure. We're going to talk about how you can determine the primary structure, which is basically the sequence of amino acids. What amino acids are there in there, and what order do they occur in? So what you want to do is you want to be pretty familiar with the various reagents that are used to determine different these different things, right? So one of the things we might want to know is what's the amino acid composition? What amino acids are present in the protein, and how many of each are there? So often the first thing you do is hydrolyze those with HCl. Amide bonds are acid cleavable. Concentrated HCl and the protein in there, you heat it up. Generally you do that to sealed ampules because you're heating it above the temperature at which water boils, so you're building up a little bit of pressure. And you convert all of the peptide bonds to free amino acids. So now we just have a bunch of amino acids. How are we going to detect them? Usually by HPLC, which is high performance liquid chromatography. And the amino acids are all slightly different in polarity. Gas chromatography isn't really useful for proteins and peptides because the things aren't volatile since they're usually ions. Right? So we separate by HPLC, but they are weakly detected in the UV range. And they're detected at a wavelength that has a lot of interference. Because common solvents like acetonitrile also absorb at 190 nanometers. Any carbonyl group is going to absorb at 190, right? So yes, the carbonyl group in the amino acid absorbs, but your solvents have to be really pure. You have to make sure there are no impurities. Otherwise, you're going to get a mess. And the molar absorptivity isn't very high, which means that you can't detect really low concentrations. So generally, we're not actually going to detect the individual amino acids. We're going to make derivatives. To improve the detection limit. And maybe enhance the separation. Right, maybe the free amino acids don't separate very well in HPLC, but if we make derivatives of them, we can get those to separate. That derivatization can happen either pre-column or post-column. So either you're going to have a chamber, right? You're going to have your flow going through here. You're going to have your reagents in here. And then you're going to put it on the column. All right, so the reagents are in here. This is a derivatizing chamber. So this would be a pre-column derivatization. Then you're separating the derivatives. And then you're going on to your detector. Or, alternatively, you separate the free amino acids And then you put it in a reagent chamber to make your derivatives. And then you go on to your detector. Right, so that would be a post-column derivatization where you're exploiting the amino acids. So what do we derivatize it with? And what's our detector? The detector is usually either UV vis or fluorescence. And fluorescence is way more sensitive. Three to 4 orders of magnitude more sensitive. So where you might be able to, with UV vis, to detect maybe 10 to the minus 4 or 10 to the minus 5 molar, with fluorescence you might be able to detect 10 to the minus 9 molar. So if you have very small quantities of your peptide, and you usually have very small quantities of your peptide, then you want to use fluorescence. Right. So first we're going to cleave them all, and then we're going to stick something in there that converts the amino acids into a more easily detectable derivative that has either fluorescence or an enhanced molar absorptivity in the UV vis. So what are those reagents? Well, there's a bunch of different reagents that are used, but two of the most common ones are N-dimethylamino 5 and N-dimethylamino, methylene, one sulfonyl chloride, and it's a pain in the ass every time you want to talk about this to write 5N-dimethylamino naphthalene 1 sulfonyl chloride. This is effectively abbreviated Dansyl chloride. And the other one that's commonly used is OPA, which is ortho-phthalaldehyde. Ortho-phthalaldehyde or Dansyl chloride. Both of those make derivatives by reacting with the N-terminus. So you'll no longer have an ammonium group. Just show the R as the side chain. So there's always some of that in equilibrium with the Zerder ion. Where you have the free amino group. And both of these reagents have the ability to react with amines but the mechanism by which they react with those amines is going to be different in those two cases. So if you were asked for the mechanism of reaction of this amino acid with Dansyl chloride, what would you do, not having seen it before? after the initial panic subsides.
I attack it with the electrons on the nitrogen, the sulfur.
So there's the nucleophile. And the electrophile is probably this sulfur. And what type of reaction is that going to be? It's going to be a nucleophilic acyl substitution. Some solvent, maybe acetonitrile. And you're going to end up with amino acid that now has this highly fluorescent tag on it. Oops. Probably be good if I left the sulfur there. And it's now actually going to be protonated. Because this lone pair is no longer basic. Since it's next to the sulfonyl group. So this is a Dansyl tagged amino acid. Every one of these Dansyl tagged amino acids is commercially available, so you can buy them. You can figure out what their retention time is on HPLC, and then you can compare the retention time of your mixture and see which ones of these shows up. This is fluorescent. And the mechanism is simple, right? It's just two steps. The nucleophile attacks the sulfur, pushes a pair of electrons out onto oxygen, and then that comes back in and boots out the chloride. So if you know the mechanism of nucleophilic acyl substitution, you could write that mechanism out. How do you make Dansyl chloride anyway? Where'd that come from? If you couldn't buy it. Well, we'll come back to that because we don't have much time left. So that's how you might expect the amine to react with that sulfonyl chloride. How might you expect it to react with OPA? So that's what the products look like of this OPA tagged amino acid. And there are chromatography columns you can buy for high performance liquid chromatography that are specifically designed to be good at separating these. So how the hell does that happen? What's the mechanism by which this becomes that? That's a little more complicated.
Is it a nucleophilic acyl chemical addition?
So this is still the nucleophile. And this is still the electrophile. So you might expect that an amine plus an aldehyde would form what kind of functional group? What usually happens when an amine reacts with an aldehyde? A what? Yep. Amide, did you say? No, not an amide.
Okay, well, the one with an I.
That would be a carboxylic acid. And not an imide, because an imide is a nitrogen sandwich between two carboxyl groups.
Then I was just
The-
kidding.
the
I
word-
was testing you.
The word you're looking for is imine.
Oh, that's the one, right?
In fact, it's going to be an aminium salt initially, right? It's going to react with the aldehyde. To form that. And you could probably do that. How many steps does it take to get from the free amine and the aldehyde to that aminium salt?
So that's 12 or something.
Nah, it's less than that. First, a nucleophilic attack. Protonate the oxygen. Deprotonate the nitrogen. Protonate the oxygen again. Lose water. And if you went all the way to the imine, the sixth step of imine formation is to then deprotonate the nitrogen to get a neutral imine. But you don't have to deprotonate the nitrogen. You can actually intercept this structure. You can intercept this structure by noticing that there's a 5-membered ring here between the nitrogen, the carbon, the oxygen, and this carbon here. This oxygen can attack that, or more properly, the pi bond can attack that. So this pair of electrons can come in here, and can come over there and attack that, and push a pair of electrons onto nitrogen. And you would then get something that looks like this. And I'm just going to rewrite it so the hydrogen's up. I've got my nitrogen here. And then that's attached to this carbon here. And look like that, where we've got our R group here. And then we've got our carbonyl. If I didn't mess anything up, it looks like that. Hopefully I didn't mess anything up. So the fact that you have that carboxylate group there greatly speeds the reaction up. OPA is not very good at derivatizing a peptide, but it's very good at derivatizing amino acids because of that participation. Someone's going to take that hydrogen off. The proton shuttle is probably that free amine. I'm going to grab that proton. I'm going to stop showing that hydrogen because it doesn't matter anymore. I'm going to stop showing that hydrogen because it's annoying, and I'll just put the R group on there. All right. So what does that look like it might be able to do? I specifically drew it so that it was right there, right? If the nitrogen can attack one, it can probably attack the other. It's going to look like that. So now you got two 5-membered rings in there. What next? Probably want to protonate that, and then we're going to want to deprotonate that. So our free amino group. Going to donate a proton to that oxygen and then yank it back off the nitrogen. To generate a neutral species again. That nitrogen back in. So it's going to look like that. Hopefully, right? Protonate, oxygen, deprotonate, nitrogen. That hydrogen that used to be the aldehyde is now acidic. This is very analogous to what we saw with this guy. Remember this guy? Where that hydrogen was acidic, and we used it to attack an aldehyde. We did this. Right? So we were able to take that hydrogen off that's adjacent, that's on the same carbon as the OH group, and stabilize it like that. We can do the same thing. This hydrogen is now adjacent to this pi bond, and we've got a great leaving group here. So we can take that hydrogen off with our free amine. And push these electrons through like this. This is basically an enol tautomer. There's two double bonds. So it will equilibrate to regenerate the aromaticity. By protonating a carbon and deprotonating an oxygen. So we take this protonate here, that puts a positive charge there, this pair of electrons can flow through. you can actually write a minor resonance structure for this. It looks like that. That would not be a major contributor, right, because that has a negative charge on a carbon. But you've got the nitrogen as electron withdrawing group stabilizing it. You've regenerated the aromaticity in the ring. So that carbon is more basic than you might otherwise think it would be. So that's how that tag happens. It's an initial imine formation, a couple of proton transfers, and then the nitrogen attacks the other carbonyl group to do another nucleophilic acyl addition. So these are nucleophilic acyl addition reactions, not nucleophilic acyl substitution reactions, and then a keto-enol tautomerization. And that's it. So I've already talked a little bit. I told you about Sanger's reagent, which is used to tag the N-terminus to determine the N-terminal amino acid. We talked about hydrogenalysis. So we'll see those again on Thursday. And then I got a couple more reagents that I want to tell you that are useful for determining certain things about peptides. And then we'll go on to the next phase of this, which is, all right, how do you make a peptide from amino acids? How do you do peptide synthesis? So that'll be the main thing. So the quiz will ask you to draw a short peptide at physiological pH and calculate its pI.